Thank you for listening to this presentation. I'll be walking you through our paper, CNN2Graph, Building Graphs for Image Classification. Before delving into the paper, I wanted to revisit the basics. One of the motivations behind our paper is this principle of i.i.d, independent and identically distributed data. This is one of the key assumptions behind many neural methods where samples are passed in and modeled independently. There are methods like v.i.t, which model intra-example information via tokenization and then applying an attention mechanism between tokens. And we use GNNs, which provide a flexible framework to explore not just intra-example information, but inter-example information. Thus, we present CNN2Graph. Our method has 6 key steps in the forward propagation. Firstly, we select C fixed anchor images, one per class to serve as class representatives. Secondly, we initialize a set of learnable proxy vectors, again, C proxy vectors to be class representatives, completely learnable. Thirdly, we embed each training and anchor example via shared backbone CNN, so we're going from our training images to embeddings. Then we construct a latent space bipartite graph, where one set is the training images and the other set is the combined anchor embeddings and proxy vectors. Finally, we compute 2 separate cross-attentions between the training images and our proxy and anchor examples, and we do a final aggregation step and pass through a linear classifier to do the classification. The motivation benefit of our approach is the following. Firstly, generally graph construction methods via some sort of selection rule limit GNNs to the transductive domain. It can be expensive to insert new nodes, but our method allows this to be done O of one time by allowing full connection to our proxy set. Secondly, prototype/proxy representations can be unstable, although useful for learning class distributions, and we've seen that anchors and contrastive objectives have stabilized their representation. Thirdly, inter-example similarity methods such as kernels and KNN generally scale poorly with dataset size, but by restricting the similarity computation, we're able to make that computation a little bit more tractable. And finally, graph construction is generally non-differentiable, but by allowing full connection to the bipartite graph, we basically explore a set-to-set operator, which allows it to be fully differentiable. Some key components that we think make our method work really well are, firstly, we use a simple combined cross-entropy and contrastive loss, which works out of the box without any tuning. Secondly, we allow separate cross-attentions for anchors and proxies, which allows the model to weight their contributions differently. And finally, our method is flexible enough to allow multiple anchors per class, which allows our model to capture variances in the class distributions. Finally, in our key results, we see that overall CNN2Graph acts as a simple layer on top of our standard backbone CNN and improves results, particularly for CNN2Transformer, over our baseline methods. We see that in particular, the experiments that try to do different proxies and different anchors, we see that can improve training. And on the right, we see our UMAP plot, where through the course of training, as the contrastive losses decrease, the latent space is reorganized to allow the proxies and anchors to group with their class. Thank you.